Thank you. Thank you so much. I'm so sorry for the schedule disruption. There have been terrible thunderstorms on the East Coast of the US that completely messed up flights. I'm really glad, though, that I still get to present my talk because the second 2/3 is all new work that I haven't presented before, and I'm really excited to share it with you guys. So for the title of my talk, I've actually stolen it from the session title because I liked it. So functional materials do something hopefully useful, right, in response to an external stimulus. And they're usually what I call complex materials. So I'll start by talking a little bit about complex materials using the classic family of complex materials, Perovskite manganites. And for the first part of my talk, at least, I'm going to keep the discussion pretty high level. I know there are people from a few different communities, so I just want to make sure that everyone stays on the same page. Right, so the Perovskite manganite family have this crystal structure, which we're going to be seeing a lot throughout my talk. The manganese ions sit in these green polyhedra. And the sites represented by these blue spheres are a rare earth cation or an alkaline earth cation. So for praseodymium calcium manganite, for example, these blue spheres would be either a praseodymium ion or a calcium ion. We care about these materials because they exhibit the phenomenon of colossal magnetoresistance. So their electrical resistivities change by orders of magnitude in response to an applied magnetic field. So these data in the middle are for praseodymium calcium manganite, and each one of those data sets shows how the resistivity is changing as a function of temperature with respect to an applied magnetic field. In conventional materials, their resistivities change typically maybe on the order of a few percent under an applied field. Complex materials often have ground states that are close to multiple phase boundaries. So when the calcium content here is 0.3, then depending on the temperature, the material is close to a charge-ordered insulating phase, a paramagnetic insulating phase, an antiferromagnetic insulating phase, a ferromagnetic insulating phase, and so on. So in these systems, changing the control parameter X, this calcium content, not only changes the whole concentration through the concentration of manganese 4+, it also subtly changes the crystal structure, which in turn affects the spin order and the orbital order. Because complex materials are close to multiple phase boundaries and have many competing degrees of freedom, their properties tend to be highly controllable with external handles like epitaxial strain, pressure, and chemical substitution. So in the plot on the right, that's for praseodymium calcium manganite, again, showing how this resistivity change with magnetic field changes with pressure. And then the response can also be tuned with chemical substitution, as we saw on the last slide. So putting all of those things together, complex materials are typically characterized by competing degrees of freedom, ground states that are close to multiple phase boundaries, and properties that are highly controllable with external handles. All of this also gives rise to the possibility for cross-coupled responses, so where electric fields can control the spin degrees of freedom, or magnetic fields can control the charge degrees of freedom, for example. These systems are usually scientifically very interesting. They usually teach us a lot about fundamental condensed matter science, and they also often have the potential to be technologically useful. So how can we find or create complex materials? How can we usefully leverage their properties? Almost everything that we do in my group is geared towards answering these kinds of questions. We're a theory group, so we use a combination of first principles, DFT calculations, phenomenology, symmetry principles, and simple crystal chemical models to explore these kinds of questions. So in the first part of my talk, I'm going to tell you about some work I did on discovering mechanisms for materials that exhibit a cross-coupled response to electric and magnetic fields. So these are polar materials. They have globally broken inversion symmetry, and they're also magnetic, and the magnetic moments couple directly with electric fields through the lattice. So these kinds of materials are known as multiferoics. I'm not really going to get much into multiferoics today. The point of the first part of my talk is really to demonstrate an approach to understanding problems, to give you an idea about how we think about these kinds of problems. And then in the second part of my talk, I want to show you how we can use the same approach in a different context to understand why some optically induced phases have long lifetimes. All right, so the family of materials that we spend most of our time working on are Perovskites, a pretty well-known family of complex materials. So this is known as the cubic Perovskite structure. It's often taken as the sort of archetype or the prototype for this family. So Perovskites have a cation on the A site, a different cation. It's typically a transition metal on the B site, and that's octahedrally coordinated by anions, usually oxygen. Perovskites are awesome because this one structure type can accommodate nearly every element of the periodic table. And that chemical versatility leads to a huge range of different properties. That list that you can see is by no means exhaustive. The other reason Perovskites exhibit so many different properties is that despite this being the prototypical cubic Perovskite structure, most Perovskites don't actually have this structure in their ground states. Because they undergo some form of structural distortion or structural phase transition. So that's a crystallographer's idea of a joke for you. The tolerance factor is an empirical measure. It relates the stability, the structural stability of a perovskite in the cubic phase to its chemical composition. So here RAO and RBO are the ideal AO and BO bond lengths. When T equals 1, that indicates that we have perfect close packing and the material is predicted to be stable in this cubic phase. When T is less than 1, then that means that the A site is underbonded in the cubic structure. So the bonds that the A site cation makes to the surrounding oxygen atoms are too long, and the material is predicted to undergo an octahedral rotation distortion, so-called octahedral rotation distortion, which shortens the length of those AO bonds. So these are the two most common space groups adopted by perovskites that undergo this kind of structural distortion. They tend not to be polar or ferroelectric, and I'll say more about them in a little bit. When T is greater than 1, that indicates that the B site is underbonded in the cubic phase, and the material is predicted to undergo a polar or ferroelectric distortion. And that's what happens in materials like barium titanate and lead titanate. So we care about these structural distortions because they can have a huge effect on the properties of perovskites, and indeed we can exploit these distortions to create functional materials. So for example, octahedral rotations, it's well known, have a very significant effect on the electronic and magnetic properties of perovskites. So for the rare earth nicolates, they undergo both metal insulator and magnetic ordering transitions. They vary from being paramagnetic metals to antiferromagnetic insulators to paramagnetic insulators as a function of tolerance factor. So the tolerance factor there is tracking the magnitude of the octahedral rotation distortion. Basically, as T gets smaller, this metal oxygen metal bond angle gets more and more bent. And you can see similar trends and phenomena in other families like the rare earth manganites. So the problem here is that most correlated perovskites or perovskites with interesting electronic or magnetic properties crystallize in this PNMA space group, which is not polar. Right? So it's not clear how we might access or manipulate these properties in a practical way. And by practical, I mean ideally electric field control. In fact, over half of perovskites, that's this big slice of the pie here, crystallize in the PNMA space group. Okay, so if we really want to achieve this goal of designing cross-coupled complex materials, then one way forward is to start with a magnetic perovskite that adopts a non-polar crystal structure and discover new mechanisms of inversion symmetry breaking. Right, so how is inversion symmetry broken in what we would consider prototypical perovskite ferroelectrics? And so in polar and ferroelectric materials, there is a spontaneous macroscopic polarization. The polarization arising from a row of alternating equally spaced positive and negative ions is zero, and we call this the paraelectric state or the paraphase. In materials with polar ground states, there's an instability such that when the ions are displaced from their symmetric positions, a polarization arises and the energy of the system goes down. So in lead titanate, in the structure on the left, it's cubic, all the ions are sitting on high symmetry sites, the polarization is zero. In the structure on the right, the titanium ion has moved up a bit. Actually, all of the ions move. This picture is a simplification. That breaks the symmetry and allows a spontaneous polarization to arise. And in lead titanate, the polarization is switchable with an applied field, so it's actually ferroelectric. The polar lattice distortion, let's call it U, has symmetry properties that are identical to the polarization, so it transforms like a polar vector. And in materials like barium titanate and lead titanate, these D0 titanate perovskites, the polar lattice distortion is induced by cross-gap hybridization between the titanium 3D states, which are formally empty, and the filled oxygen 2p states. So the instability that gives rise to the polarization is associated with an unstable IR active phonon of the paraelectric structure. So if I look at a toy model of a phonon, I have a ball sitting in a potential well, it's oscillating back and forth about its equilibrium position. I can calculate the frequency of that oscillation, which is proportional to the curvature around this point. And if I do that, I'll find in this particular case that the frequency squared is positive, indicating that the material is stable towards this particular structural distortion. So if I displace the ions along this coordinate, the energy goes up. If, on the other hand, the underlying potential at t equals 0 looks like this, so if I put my material into the structure that corresponds to this saddle point, this is the high symmetry paraphase, and calculate the curvature around this point, I'll find that the frequency squared is negative, indicating that the material is unstable towards that particular structural distortion. Okay, so this is what's known as the soft mode theory or the soft mode mechanism of ferroelectricity. And over the years, people have come up with a number of different strategies for inducing polar lattice distortions in nominally non-polar or non-ferroelectric materials based on this mechanism. The problem is that those strategies are not really amenable to inducing cross-coupled complex materials. So can we find alternative mechanisms that are? And just to give a teaser, answering that question is going to lead us to a novel form of inversion symmetry breaking in layered perovskites. So it was a theoretical prediction first, and then experimentally demonstrated a bit later in this Ruddleston-Popper phase material. And these images just show some of the beautiful and very rich domain structures in this material, and some equally beautiful polarization hysteresis loops. So this material is actually ferroelectric. So this novel form of inversion symmetry breaking is going to enable exactly the kind of cross-coupled materials that we're after. But before we get to that, it's helpful first to understand this question. So why are the majority of perovskites not polar? Right, so say you have some system, some material, and you're interested in understanding why does this system behave the way it does, or why doesn't it behave in some other way? Why doesn't it have some properties that I want it to have? So what can you do? Well, we have very powerful experimental and theoretical techniques these days. We can do various physical properties measurements. We can calculate various properties with higher accuracy than ever. We can try changing the composition and studying how the property of interest changes as a result. You can do all of those things. You can also do something that might seem a little counterintuitive at first. You can restore symmetries that are broken. So there are systematic group theoretical techniques you can use to do this in a formal and rigorous way, which is what we do. But here I'm going to describe this in a conceptual way to give you the big picture, and then all the gory details are down here in these references. Right? So we have this system here, this low symmetry structure. And if we just look at it, so what can we see? Well, we can see that those green polyhedral units are kind of tilted and rotated with respect to each other. And it seems as if we could unrotate them, then we would restore some symmetries and end up in a higher symmetry space group. And then this is more difficult to see from this image, but these cations here are also offset from one another in the layers. And so if I make them all line up, then I can restore some more symmetries and go to a higher symmetry space group. And so you can keep doing this until you can't make the symmetry any higher. And then this is the high symmetry reference structure that you end up with, the high symmetry paraphase. And the low symmetry structure is in a subgroup of the space group of the high symmetry paraphase. Right? So the high symmetry paraphase might actually be in the phase diagram of your material. It might be some high temperature structure, or it could just be a virtual reference structure. For our purposes, it doesn't really matter. The structural distortions that relate these two structures are known as modes. We can often associate them with phonon modes of the high symmetry paraphase. They transform like some irreducible representations of the paraphase. And we can treat those modes as kinds of order parameters in a Landau theory. So we can expand the paraphase, expand the energy of the paraphase in powers of these modes. And the form of that expansion gives us a lot of information about how various modes are coupled together, and about the mechanisms through which symmetry breaking happens. Right, so what are the precise structural distortions then that relate these two structures, and what can we learn from that? Okay, so I've mentioned octahedral rotations and tilts a number of times. So if we start from the cubic structure and add these two particular rotation distortions, these are rotations about different crystallographic axes. These are their IREP labels. then we get the PNMA space group symmetry. So those two distortions by themselves establish the PNMA space group symmetry. But that doesn't mean that other kinds of structural distortions aren't present and aren't allowed by symmetry. So indeed, if we look at all the structural distortions that are allowed by symmetry in PNMA, then you see that there are also these what we call antipolar displacements of the A-site cations. And if we expand the energy about the cubic phase, then there is a trilinear term that couples all three modes together. Okay, so what that means is that if one of those distortions condenses, then the other modes get pulled along. Right? So they're anharmonically coupled. Okay, so these A-site cation displacements actually induce a polarization in the AO layers. So they induce these little layer dipoles. These data are for strontium stenate. The precise material choice is not important here. But because the A sites are related by inversion symmetry through the B site, the polarizations that get induced are exactly equal and opposite, and they cancel each other out. Macroscopic polarization is zero. In fact, you can show that these A site cation displacements suppress distortions that globally break inversion symmetry. And so the most straightforward thing that you can do is simply to replace every other layer of A-site cations with something else. So for barium, for example. So now when those cations displace, they will displace by different amounts. And the polarizations that get induced are now not exactly equal and opposite. And so there's this residual or leftover non-zero macroscopic polarization. If the cation on the B site is magnetic, then the polarization and the magnetization become coupled through the lattice. And again, there's a trilinear term in the energy expansion about the high symmetry paraphase that couples together the two rotation distortions, R and M, plus the polarization, right? Such that if one of these modes condenses, then the other two get pulled along. And if one of these modes changes sign, so if the polarization changes sign, through an applied field, for example, then one, but not both, of these other distortions will also change sign. So this form of inversion symmetry breaking is quite different to the Salk mode mechanism I mentioned a few minutes ago, because it relies on a coupling between different distortions that are non-polar individually, the rotations, but that combine to produce a polar space group, thereby inducing a polarization. And because these distortions are coupled to other properties like weak ferromagnetism here, it gives rise to exactly the kind of cross-coupled materials we're looking for. And so there's been a ton of work around this mechanism since I first started working in this area that I don't have time to talk about. But if you'd like to know more, my long-term collaborator, Mike Haywood, and I published this review last year that surveys what's been done in the area from the perspective of theory, computation, and experiments. And so what I'd like to show you now is how we can use this way of kind of thinking about things to enable control of properties where light is the external handle. And there's a specific kind of experiment that we're interested in. It's known in the literature as nonlinear phenonics. So I know a number of people there are familiar with this experiment and do these kinds of experiments in their labs. But again, in case you're not, here are the main points. I just want to go over them quickly. So here's an example of such an experiment on praseodymium calcium manganite. And here is this phase diagram again, showing that when X is 0.3, the material is sensitive to external perturbations. And I'd also like you to notice that the material is insulating over this whole section of the phase diagram. So what was done in this experiment was that a laser was tuned to the frequency of a phonon mode involving displacements of the manganese ions opposite these oxygen atoms. And after exciting this phonon, these authors see a change in the reflectivity of the material that is consistent with an insulator to metal transition. And this metallic state persists for quite some time after the initial light pulse. And by varying the wavelength of that incoming light pulse, they see that the maximum change in conductivity occurs at the energy of that 71 millieV phonon mode. Okay, so the interpretation of what's going on here is that the lattice is playing a dominant role in this transition because electronic excitations are gapped at these frequencies. Okay, so the atomic displacements that accompany these phonon modes change the crystal structure in such a way that it's no longer insulating. And there have been a bunch of other experiments like this, one of which we'll see in a second, looking at different properties. This was just one example. So this is a cartoon. It's very cartoony of the nonlinear phenonics mechanism that was proposed to explain the results of the experiment that we just saw. So a laser is tuned to the frequency of one of the IR active modes in the material of interest. That light pulse resonantly excites that mode, which then starts ringing because we've just dumped a whole lot of energy into it. The IR active modes are coupled to other modes in the material in a way that depends on crystallographic symmetry. And because this coupling exists, the ringing IR mode creates a force on modes that it's coupled to so that they also displace. And this displacement of atoms can change the properties of the material. So in the early nonlinear phenonics work of the modern era, the specific coupling term that has probably been most well investigated looks like this cubic term. So here, QIR is the amplitude of the IR mode. QR is the amplitude of a Raman mode. So these papers were looking at all the modes, all the relevant modes were at the zone center. And A is a coefficient. Its value is material dependent. It tells you how strongly coupled those modes are. As you'll see a little bit later on in my talk, though, other kinds of coupling term are definitely allowed and turn out to be way more important than this cubic coupling. Right, so usually at this point I say, well, in a real material, the vibrations don't go on forever. The energy that we put in the form of the light pulse has to go somewhere. Eventually it'll get turned into heat. And we're interested in the transient response of the material before thermalization. The timescale on which that happens will depend on the material, but usually it's somewhere around sort of picoseconds to maybe a few tens of picoseconds. The rationale for saying that is that, if you look at this mechanism, if the ringing IR mode creates a force on these coupled modes that causes them to displace, then when the IR mode gets damped, the coupled modes should also ring down. But if we look at the observed lifetimes in some of these experiments, 500 picoseconds, 1,000 picoseconds, this is orders of magnitude longer than the typical optical phonon lifetime. Okay, so these lifetimes of these metastable phases can't just depend on the IR mode lifetime. It has to be something else. So we think we have a tentative answer to these questions now. And for this work, we've really been focused on this experiment on lanthanum aluminate, which was done in the group of Andrea Caviglia. So he's very conveniently there. So any thorny questions you have about the experimental setup, he's very conveniently there to answer them. Right, so at room temperature, lanthanum aluminate adopts this rhombohedral structure with octahedral rotations in space group R3 bar C. The octahedra are rotated about the cubic, pseudo-cubic 111 perovskite axis. So for you, that's the direction coming out of the screen. We say that lanthanum aluminate is boring in a good way. There are no other structural distortions present apart from the rotations. The band gap is pretty big. It's over 5 eV. Electronically, there's not much going on. So this is great for us because it allows us to really focus on the response of the lattice to optical excitation without worrying about a bunch of other stuff. So what was done in this experiment was that a pump was tuned to frequencies from 17 to 41 terahertz. There is an IR active mode at about 21 terahertz. And when that mode is resonantly excited, then there are multiple long-lived oscillatory responses. Right, so this inset is the Fourier transform of this reflectivity data. This 1.1 terahertz oscillation was assigned to a Raman mode with EG symmetry. Its response is strongly temperature dependent, and it has a lifetime of about 20 picoseconds, just based on the reflectivity data. And then these lower frequency responses are assigned to acoustic modes, and they live for much longer, up to 1,000 picoseconds. All right, so this is the model that we set up to do this work. There are a lot of complicated details, so I'm just going to sketch the key points here. The basic idea is that we have a phenomenological model which is parametrized using first principles calculations, and then the output of the model, which is mode amplitudes as a function of time in response to optical excitation, gets fed back into first principles calculations. Right, so we start by expanding the energy of the equilibrium crystal in powers of various modes, which we kind of consider as order parameters. So as the high symmetry paraphase, we take the equilibrium unexcited crystal structure. So this is a particularly simple expansion that we used in previous work just for illustration purposes. The one that we developed for the current work is more complex. So the Ks here are second order force constants of the relevant modes. The Qs are mode amplitudes. We calculate both of those things from first principles. In this simple model with two different modes, and for a material of this particular symmetry, the lowest order coupling was this cubic coupling that you've already seen. And the kinds of terms that you can have in this expansion are determined by crystallographic symmetry. The last term on the end describes the coupling between the electric field of the incoming light pulse and the polarization change in the crystal. Z star tilde is the mode effective charge. It tells you how strongly the IR active mode, the pumped mode, is coupled to the incoming light pulse. Nonlinear terms in the polarization can be important. That's explored more in this paper, but for this particular work, we just cut the polarization off at linear order. So we include IR modes at 18.9 and 19.1 terahertz. There's two different symmetries. These are their irreducible representations. We include all Raman modes. So gamma 1 plus, this is a rotation about the 111 pseudo-cubic Perovskite axis. Gamma 3 plus is what's called the EG Raman mode in Andrea's paper, and we include all the allowed strains. We include all symmetry allowed couplings between the IR modes, the Raman modes, and the strains up to third order. And we excite at 19 terahertz with 200 femtosecond pulses, and we pick up components of both sets of these IR active modes. So in our previous works, we didn't include damping, but in this work, we're explicitly interested in lifetimes. So we really need damping in our model. The equations of motion for each mode are derived by taking derivatives of the energy that you saw on the previous slide. So this is just F equals ma. And in the phenomenological spirit of our model, we add this dissipative force for each mode. The gammas are 3 phonon scattering rates, and they are calculated directly from first principles. Before looking at the dynamics in detail, that we wanted to check that we were on the right track. So we compared some of our data to those reported by Hortensius. So the plot on the left shows the lifetime of that 1.1 terahertz e.g. Raman mode as a function of temperature. So our data are in blue and the experimental data are in orange. And then for the plot on the right, that compares our amplitudes, a normalized amplitude for that mode as a function of temperature with the data from experiments. So in both of these cases, I think we're capturing sort of key qualitative trends. So this gave us confidence that our model is giving us sensible results. So these kinds of data don't just fall out of a routine DFT calculation. There's quite a bit of extra work involved in getting this kind of information. So it's highly unlikely that we got these results just by chance. And so once we were convinced that everything was working the way we thought it should, we started exploring the influence of different pathways and couplings on the dynamics. So we have these 3 groups of degrees of freedom or order parameters, the IR modes, the Raman modes, and the strains. All of these things can couple together subject to crystallographic symmetry, energy, and momentum conservation. So in the following slides, we're going to explore what happens with the dynamics when some of these pathways or couplings are switched off. So in the first set of data that you'll see, we only allow coupling between the IR and the Raman modes, which means that we have terms that look something like this in our energy. We have many more terms because we have lots of modes, but they're going to be some IR mode coupled to some Raman mode at some order. In the second set of data, we switch on coupling to strain through the Raman modes only. So then we'll pick up terms that look something like this. So these epsilons are strains. In the third set of data, we'll have coupling between the IR modes and the strains. So the Raman strain pathway will be blocked. And then in the final set of data, we'll allow all the couplings. Okay, so this top panel here shows the Raman modes in response to optical excitation. The orange is the gamma 3 plus or the EG Raman mode. The blue is the gamma 1 plus mode. These data go out to 20 picoseconds, but we ran the simulation for much longer. The second panel is the strain amplitudes. And then the final 2 panels are the Fourier transforms of this data. Okay, so when we have just IR Raman coupling, then the modes, Raman modes ring at their equilibrium frequencies. There are also these low frequency components. In this particular data set, I don't think these are real. These will go away with damping. but there are some real low frequency components that develop, which you'll see in a minute. So nothing too mysterious going on here. Obviously, the strain amplitudes are 0 because we're not allowing the coupling to strain. And so now in this second panel, maybe you can see here that the Raman oscillations have changed a bit, and now the strain amplitudes are not 0 anymore. So again, the Raman modes ring at their equilibrium frequencies. So here's that 1.1 terahertz oscillation. And then they also develop low frequency components through coupling to the strains. And then the strains also ring at those low frequencies. When we allow coupling to strain through the IR modes only, the strain amplitudes get much bigger, as you would expect. And then when we allow coupling with everything, the qualitative picture doesn't change too much from what we saw if we just have Raman strain coupling. So the main things that we get from this are the strain modes ring at low frequencies. That is exactly what you would expect, nothing surprising there. And then the Raman modes develop low frequency components below a terahertz due to bilinear coupling with strain. So I haven't shown this here, but we looked at what effect the higher order coupling to strain has, and it's not doing very much. Those low frequency components of the Raman modes are coming about because of this low order coupling to strain. And so now we're looking at the same thing again, but with damping switched on. And now this axis goes out to 200 picoseconds. So when we have just IR Raman coupling, the Raman mode rings down in about 40 picoseconds-ish. This data is at 40 Kelvin. And the Raman modes only ring at their equilibrium frequencies. When we allow coupling to strain through the Raman modes, then we start to see these low frequency components coming in for the Raman modes. They go away if we only allow coupling to strain through the IR mode, although, as you would expect, the strain amplitudes get much bigger. And then if we allow coupling with everything, then amplitudes get bigger, but the qualitative picture doesn't change very much. Right, so again, those Raman modes develop these low frequency components due to direct bilinear coupling with strain. Those components disappear when the Raman strain pathway is removed. Right, so far I've talked about, what the spectra of the Raman modes look like and the strain modes look like. But I haven't really addressed this 1,000 picosecond lifetime for this optically induced phase and why it's so long. Is it just the strains that are out there that are causing that, or is there something else? Okay, so this is my last slide. This data set comes in two parts. So the top panel, this is just the spectra of the Raman modes. The top panel shows the Fourier transform taking only the first picosecond, 5 picoseconds, 10 picoseconds, etc. Of data. And then the corresponding bottom panel shows the Fourier transform taking everything except the first, say, 10 picoseconds. So this is from 11 picoseconds out to 1200 picoseconds. So breaking things up like this lets us see when particular signals come up and when they die away. Right, so those low frequency components of the Raman modes, they appear in the spectra by about 5-10 picoseconds. But by about 20 picoseconds, that 1.1 terahertz oscillation is starting to die away. And by 40 picoseconds, that oscillation has pretty much completely been damped out. And that's consistent with what's seen in experiments, but those low frequency components are still very much there. By 500 picoseconds, the orange mode, the EG Raman mode, has been damped out, but the gamma 1 plus Raman mode is still there because it couples to a strain that is longer lived. And then by about 1,000 picoseconds, everything has been damped out. Right, so I think the main message here is that strong coupling between different degrees of freedom, so Raman modes and strains in this case, provides a mechanism through which optically induced phases can have long lifetimes. I think it's plausible that this mechanism can operate in different materials. I don't think lanthanum aluminate is special in that sense. So this is my kind of main, one of my main take-home messages. And the other one is that in complex materials, even tiny structural distortions can qualitatively change physics and properties. That the crystal structure is as important as electronic structure. That's going to be carved into my gravestone. And I just want to acknowledge the people who did this work. So these are my group members who work on this kind of stuff. And the work that I presented on lanthanum aluminate was done by Sabrina Lee. It was not easy to do that work, and she did a really tremendous job. So I just want to acknowledge her efforts. And I will finish up there. I'm happy to answer any questions. Thank you very much for your attention.